In this video, I'll be bouncing characters on an LCD screen, Z80 style. So I finally got my hands on one of these LCD displays. It's a 20 character by 4 down, 20 by 4 LCD, slightly bigger than the usual 16 by 2. And I thought, what can I do with this LCD screen that will be interesting enough and that hasn't been done, at least in popular LCD videos. Now there's a ton of LCD videos online on YouTube that goes through how to send characters to the screen and can control them. So I'm not going to go through the basics, you can watch them. But I thought, I've been playing with particle animation, balls, and physics regarding bouncing balls off each other. I thought, well, so let's try to do a bouncing ball program on the Z80 using the LCD screen, where characters can bounce off the walls and hit each other and bounce back off. So I don't think it's been done before, at least the videos that I've searched, so let's give it a go. Now there's a couple go-to YouTubers that I regularly watch. One is the One Lone Coder and the other is the Coding Train. Now they explain these particle physics in much better details than I will, and if you're into programming, these two channels are a must watch. So before we get started, we need to hook this up to a computer of some sort. An 8-bit computer is easy enough because it's 8 data lines to feed into the LCD. Let's have a look how I'm going to connect this up to the Z80 computer that I've got. Connecting an LCD to your computer is really straightforward. Pins 1 and 2 are just the power lines, 5 volts and ground. Pins 3 is the contrast line. Connecting it to a 10K trim pot works well to change the contrast. Pins 7 to 14 are the data lines. That's just directly connected to your data bus or your parallel port, whatever you've connected it up to. And pins 15 and 16 are for the backlight. Sometimes this is connected to a switch so you can turn that on and off. But the 3 important lines are the ones in green. Let's go through them. Pin 4 is the register select. A high there means it's data that we're transmitting. Data means a particular character that you want to display on the screen. And low means it's an instruction, something like clear screen or set up the configuration of the LCD or to move the cursor around on the screen. Pin 5 is the read-write line. High means read, low means write. This is directly connected to the read line of the CPU. By default it's active low, so connecting it to an inverter works really well, especially with the timing. And pin 6 is the enable line. That just turns the LCD on and off, ready to accept data. As multiple devices are connected to the data bus, we only want to activate the LCD when we're sending data or reading data from it. And this is normally connected to the IORQ line of the CPU in conjunction with the address lines, usually on an 74LS138 chip. I've just got this connected to port 4 on my tech, but you can connect it to whatever you like, and also A7 for the register select. Again, that could be something you can change to your configuration. How do we send data to the LCD via the Z80? Here's some examples. First one, load A with 1. I want to do a clear screen there. O1 means clear screen. And we use this out command. Now the out actually does 3 things in one go. By using the term out means the read line will be high, which will mean it's a write. O4 is the address. So 0 at the front means A7 is low, it's an instruction, and 4 is the port. And A is the data. If we want to send data out to the screen, let's say the letter X, we load it to A, and we just set A7 to high. That tells the LCD it's the data. And you can't just keep hammering the LCD with information. It does get busy from time to time. We need to check before we send data to it. Check the busy state, and we do an in command there. That will actually set the read line to low, which will enable the LCD for reading. And it's an instruction 04. Once we get the value that it sends back in A, we check bit 7 to see if it's busy or not. Have you been dreaming of that electronic project and want to make it a reality? Just like my ultimate expansion board for the Tech 1F. Well, head over to PCBWay to make your dreams come true. PCBWay are the leading printed circuit board manufacturer. They make high-quality multi-layer boards with a 24-hour production time. Just enter the board dimensions and upload your Gerber file, and that's it. Once posted, a neat box will arrive with your well-packed goodies. Just look at the quality of this board. They also do PC board assembly, CNC machining, and 3D printing. You can even order user project boards directly from their website. For $5 off your first order, click on the link below. PCB Way, prototype, the easy way. So this is the ultimate add-on board for the Tech 1F. This is a Talking Electronic Z80 computer. It's a board that I've developed. It has three main features. One is to connect the LCD up to the computer, either a 20 by 4 or a 16 by 2. Also an 8 by 8 LED matrix, a single stepper with other various interrupts. It also comes with an expansion ROM as well, but what we're interested in at the moment is just the LCD connection, the inverter, and the 10K trim pot for contrast. But you don't need something fancy like this. My test rig was just a breadboard where I can just slot the LCD into the breadboard and test. This is the completed board. The LCD sits on top. Now, for whatever reason, I decided to put female on top, so I guess I prefer females on top. And the female connector goes in like so and pushes it down. So how does this connect to the Tech 1F? I've got these females again, female connectors, and it slots straight onto the board. So this is the Talking Electronics Z80 computer. That's the computer that I'll be using to program the LCD. You would have seen this before in my previous videos. I've got header pins here that connect to the CPU pins and the address and data pins over here. This board just simply slots on the top of all these components, just like so. Push it down and it's ready to go. Let's fire this up. What you see now on the screen is the default BMON LCD readout. It's just showing the next 8 bytes stored at address 2000. There's 5 things here that I need to work out to get this physics engine working. The first thing is, how do I send information to the LCD to set it up? How am I going to display the character at a particular location that I want it? How do I actually move the character, bounce it around? Also bouncing off the walls, X and Y walls, and also lastly bouncing off each other. So we're going to go through that now. Let's have a closer look at the LCD layout. Now we know it's 20 characters by 4 across, and each character usually has a letter in it. Hello. Now if I want a ball and I want to move this ball around the screen, since the character space is so small, it's just going to be impossible to do. I mean, let's say I want to move this ball upwards by 5, well, it'll bounce off and come back down again. You won't even see the bounce. There has to be another way. Let's have a look now at the individual characters on the screen. How are they created? So each character has 5 pixels across and 8 pixels down. So if we've got 20 by 4 characters and 5 by 8 pixels across, that gives us a total of 100 pixels across and 32 pixels down. This is a much better way to define my ball movement. I've got a much bigger area to play with. So all I need to do is when I move the pixel, I then need to just map it back to the character. So from pixel space to character space. How is that done? Well, really easily. Let's assume B is the X coordinate in pixel space. I know there's 5 pixels across on the X axis per character. That's in E. I reset B to be FF because the next line is increment. And then I just keep subtracting the pixels, 5 from the pixels of the B coordinate. And each time I do that, I increment B by 1. If A isn't 0 or negative, I just repeat the process. And then I just do the same thing for the Y coordinate. Once I got that character space value, I need to work out how to put that on the screen. Remember, we've got a 20 by 4 array here. All we've got to do is pick the location on the screen to move the cursor to, and these locations are defined by these hex numbers as an instruction. So let's say I want to place the character in column 10, row 2. Well, first I get the right row. So in a lookup table, I'll retrieve C0 for row 2, and then I just add the number of characters across. In this case, will be 9 because we started with 0. It gives me C9. In the code, all we do is send C9 out to the LCD as an instruction. That will move the cursor to position C9, and then we just send the character, let's say T, as a data. Okay, I've got a ball now here displayed at the top left-hand corner, 1X, 1Y. Now remember, I've got 5 characters to move across and 8 characters down for it to go to the next character position. Although you can't see me press any buttons, but you can hear me. It's 1, 2, 3, 4, 5, and it moves. So that's showing I can do 5 across. Let's do another 5. 1, 2, 3, 4, 5. Moves. Let's go down. We need to go 8. 1, 2, 3, 4, 5, 6, 7, 8. Perfect. And 5 across. 1, 2, 3, 4, 5. And let's go up now. Just 1, because it was at the top section of the 4th character across. So that looks like it's working well, although as you can see there's no clearing up of the ball, but the ball is moving. So this is where the physics comes involved with the ball movement. There's probably others who can explain this a lot better than me, but this is the basic principles of moving something in a 2D space. Let's say we've got a ball in position 2, 2 on a Cartesian plane. So x is 2, y is 2, and we want to move this. So we need to move it in a particular speed and direction, and that's called a velocity. In this case, this velocity is to the bottom left-hand corner, -2 and -2, in that direction. The velocity also determines the speed as well, so the longer the arrow, I guess, the faster it goes. But what about external factors like acceleration, deceleration, gravity? Well, we'll add the acceleration onto the velocity. And for instance, gravity could be -1 in the down direction. So velocity plus acceleration is, in this case, -2, -3, and then we add the velocity to the ball, and it moves to its new position. That's the basic principle of movement using velocity and acceleration. So one ball by itself would be pretty boring. It needs to have multiple balls. This is how I've set up the ball data. Now obviously we need the X and Y position of the ball in pixel space. So remember there's 100 across and 32 down. In hex that's 64 across hex and 20 hex down. We also need a velocity, which we've just talked about. Now I've got 7 and 2 here. What does that actually mean? I'll explain that later. But because on the Z80 we don't have floating point numbers out of the box, in terms of the velocity, I've combined into 2 parts. So the direction and also the rate of change, or the speed. And how this works is that once the change timer is on 0, I move the ball. And once I do move the ball, I reset the change timer to the rate of change, which is in this case 40 hex. And each cycle of my draw move loop, I decrement the change timer by 1. So the higher number of the rate of change means a slower speed or a smaller velocity. And this also gives me the ability to change the rate of change during the program to make the balls faster or slower. And lastly, have the ball character, 1 byte worth of any character you might want to represent as the ball. To access this ball data, I use the IX register, because that has indexing. It makes it a lot easier to access each of those parts of the ball. So for instance, if I want velocity, I just add 2 to the IX register. IX starts at the position X, or the first byte of the ball. Velocity is 2 across, we start with 0. And speed, if I want the speed timer or the change timer, I go to IX plus 5. And then when I get to the next ball, I just increment IX by 7, which is the next ball across. So ideally I've got a ball and I want to move it in 16 different directions. When do I want to move it? Well, when the timer goes to 0. How is that done? Easily. I get the timer, I check if it's 0, or A sets the 0 flag if it's 0, if the value of A is 0, and if it is 0, I move the ball. Otherwise, I decrement the value in the timer by 1, and I skip the move. Now obviously in move ball, once the move is done, I replace the timer with the rate of change to restart the timer. What about those numbers, 1 to 7? Well, this is what I've determined to make it easy to use the first 3 bits of a byte. And I've decided that number 4 will be no movement at all. Number 1 will be fast to the left or downwards. Number 7 will be fast to the right or upwards. So how do I use this velocity to actually move the ball? I first get the velocity value. I subtract 4 from it to normalize it, to give it into the negative state or the positive state. And if it's on 4, it would be 0. I just save that value in B, I get the current X position, and then just add it. And yes, if you add a negative number to A, it'll be just like subtracting it. So for instance, if I had the velocity as 2, I subtract 4 from it, that gives me FE, because it cycles around the 256 bytes. Adding FE to A would actually subtract 2 from A. So this works perfectly, and that moves the position. Alright, bouncing off walls. This is really straightforward because one object is static and the other one's moving. Let's say we've got a ball and it bounces off a wall. All we need to do is reflect it on the x-axis. This is an x wall, and we reflex it off the y-axis if it bounces off a top or bottom wall. All we've got to do is change the velocity in the other direction. Remember those velocity numbers, 1 to 7, 4 is static in the middle, 1 is fast to the left or down, 7 is fast to the right or up. We just need to swap those numbers around, 1 to 7, 2 to 6 and 3 to 5. So how are we going to do that on the Z80? It's actually really simple. We get the velocity, this is just for the X component, and all we do is negate it. That gets the 2 complement of it, and then we mask out the higher bits. So we just keep bits 0, 1 and 2, and that's another reason why I've chosen 1 to 7 as the velocity directions. It just makes programming it more simple. And lastly, we just load it back to the velocity, and next time we do a ball move, it will move in the other direction. Alright, so I've loaded up the program to bounce the ball off the walls and move one ball around. I've set this ball up to move in this direction down here, so let's now run that. And that looks like it's moving quite well around the screen. It's got nice right angle bounces, left and right, contained within the LCD. Now it's a bit jaggedy because of the 4x20 layout, but that's actually working quite well. Alright, so let's try 8 balls and give that a go. There you go, bouncing balls, moving around the screen. It wasn't that difficult to do. Setting up with the right configuration, just some simple movements. But I can kind of see a problem here. There's no collision detection amongst the balls, and they're actually merging into each other if they own the same character space. So probably the hardest part now is to try to figure out how these are going to collide and what angles they move, because it's not just a static collision against the walls, that's like a right angle or reflect angle. We need to work out how, when they do collide, how we're going to bounce them off each other. So let's now look at how to do that. So to prove that they're actually going through each other, instead of just having the same character of a ball shape, I've got A and B here. Let's run them into each other and see what happens. They should just phase through each other. And as you can see, they bounce off the walls, but not each other. Now we need to fix that. Static collisions are straightforward, but what about elastic collisions when two balls bounce off each other? This is a bit more trickier. So we have two balls, and they move towards each other in different directions. Their velocities are slightly different, so B1 is going to the bottom right, B2 is moving across to the left. What we need to look at is the impact and what the changes make on each individual ball. I'll call that kinetic energy. To do that, it's a simple formula. We subtract the velocity of ball 2 with ball 1. So what does that give us? 2 minus minus 1 and minus 2 minus 0, which makes the difference in the collision energy is 3 and minus 2. What do we do with that? Well, for ball 1, we just subtract it from ball 1, and for ball 2, we add that kinetic energy to ball 2. Now, I've really dumbed this down a bit in terms of how the impact works. I consider that each ball is the same mass, and there's no gravity or friction to slow the balls down. This is purely two balls colliding with each other in a vacuum of space. So what do we get with those calculations? Simple calculations. Ball 1's velocity is now -1, 0, and ball 2 is 2 and -2. Now those numbers actually look familiar because they're the opposite of what we started with. Ball 1 now moves in the left direction, ball 2 moves in the bottom right hand direction. So all we need to do for a simple bouncing calculation is just swap the velocities around. And this is the code that does it. I get the ball 1 velocity x and ball 2 velocity x in A and B, and then just save it back to the opposite ball velocity for the x. And I do the same thing for the y. And that simple ball collision, it's really not that difficult. Alright, so I've loaded the code up with the collision detection now, ball collision. Let's face these two balls, A and B, off each other, and they should bounce back off each other. Let's give that a go. Yep, A and B bounce back off each other. A and B. Bang, that looks like it's working really well. Let's just try now changing the velocity of A and B to a different angle, and let's see how these two balls will respond when they hit each other. Alright, now let's give that a go with the different direction. Got A and B, yeah, they look like they're colliding. Yep, there was a collision there, another collision, and another one. So that looks like the basic is working. Let's now add a whole bunch of more balls and see what happens. Alright, here we go. As you can see, it is working. They are bouncing off each other, but some are still melding into the same character space. I know the formula that I'm using isn't perfect, but it's, for this simple example, they are bouncing off each other, independently moving around. I'm pretty happy with this result. With collisions, as there's two balls involved, I don't want to repeat comparing ball 3 with ball 2 and then ball 2 with ball 3. So I just iterate through the balls one at a time in a particular order that I only see those combinations once. And here's a little table that I just put together comparing each ball and make sure I only do it once and don't double up. How it works is that I get the pixel space and I convert it to character space, and if they're the same character or they're in the same character position, then it's a match. And from the match, I've got the two different codes here. One is the calculating the kinetic energy and then subtracting it from ball 1 and adding it to ball 2. But another way to do that is what I've shown before, is just swap the velocities around for each ball. So X velocity and the Y velocity. And then I just get the next ball until all collision checks are done. I guess for next steps, what you could do is you can actually create custom characters, not just the standard ASCII characters, and use individual pixels to move around the screen to actually give it a much better flow with the movement, because it's a bit jerky being 4x20. And I guess that's for another day. Now in the code, I've got an example of how to set up different custom characters. In fact, let's load some of them up now. Alright, as you can see, you can be quite creative with the LCD, custom characters, create whatever design you like. It's all there in the code. Well, I hope you've enjoyed this video. I thought it would be quite difficult to do to start with, but it's pretty straightforward after you taking step by step, building the process. So hopefully you guys can get yourself an LCD screen, connect it up to your 8-bit computer and play away. This code can be easily ported to different microprocessors. So thanks for watching, and we'll see you next time.